Starting the recording. Yes, so recording has started. Okay. So please confirm once again that the screen is visible at your end.
Yes, sir.
Yes, sir.
Okay, thank you. So in the last class, we have discussed about the question number one, and this first four circuits, right? This one, this one, this one, and this one, right? I hope there is no doubt for this first four questions. This four, figure 1A to figure 1D. Here we have to find what is the output voltage or what is the expression of output voltage, okay, for these six circuits using op amps, right? So then let us see the number five one. Number five is figure 1E. So here you can see this 5 volt is being connected with in this configuration. So again here negative feedback is there, right? With a resistance of 5 kilo ohm, it has been connected with this terminal, and with this 4 volt, it has been connected with this. Right, and here we have two resistances RA and RB, and we have to find the output voltage. So this is that question. So here the important thing is that like here we do not know actually what is. Okay, let us see that. Okay, so let the potential this of this node A. So let us say that this potential is Vx because we have to find this potential only, right? So the potential of node B, that is this is the node B, that will also be this Vx, right? Because of this virtual short concept, right? So if this is Vx, this is Vx. So the other way, we actually see here this 4 volt is been connected with 5 kilo ohm, connected with the op amp, non-inverting terminal, but at the same time, one another resistance is also connected. So that way we cannot say what is the voltage by looking at it, right? So like for example, when we are doing it here, right, we can say that this potential is 4 volt. So definitely we can say this is at 4 volt. But for this circuit, it is a bit different. We cannot say that. So we are saying that these voltages are Vx. So that way, what we can write, say this is for this part. This is okay, 5 volt minus Vx, 5 volt minus Vx by the resistance R1. So that gives the current which is flowing through this. So this current would be the current which is flowing through this 40 kilo ohm resistance. So it is Vx minus this V output. This voltage is V output. So Vx minus V output by this resistance R2, right? So here you can see from this we can get a relation between this Vx and the output voltage and the resistances, right? So similarly here if you apply this in again like considering the voltage as Vx, then what we can see here, this 4 volt, right, minus Vx by this 5 kilo ohm resistance, that is the Ra, right, that gives this current. So no current can flow inside op amp, so this current would have to be flown through this, right, the like through this RB only. So it is basically Vx. If we consider like this is the common potential, this is the ground potential, so it is this Vx minus 0, so the Vx by RB, right? So this is the another, this is another expression that we are getting from here. So from here we can get what is the value of this Vx. So here see Ra, Rb, every values are like all the values are given. So if these values are given, again, okay, from here, then you can actually put those values here, right? Here only unknown is this Vx, right? And you will get the value of this V output. So that way you can find the value of V output. It's quite easy. So similarly for question number question number this 1 6, here the again the same question is same, the output voltage we have to find, right? Here the input is 5 kilo ohm been applied here, and this other the non-inverting terminal has been grounded. So this is the zero potential, so this will be at the zero potential. Again the same thing, 5 minus 0 by R1 is the 10k, so this gives this current I. But here the at this output the scenario is a bit different, right? Here there are two op amps. So first stage we are considering it as V output, second stage we are considering the voltage as Vx. So if we consider like this current, right, this current would be equal to the current flowing through this as well as the current flowing through this, right? Because the current here the current I is coming, right? Then it will divide between these two points. So it is V output minus 0. So this is this V output minus this 0. This is the opposite. This is basically we are doing the applying the KCL, right? The V output minus 0. So we are taking the current in this direction, right? And the other case, it is basically Vx minus 0 by this 80 kilo ohm. That gives us one equation from here, right? And this basically relates this Vx with this V output, right? Similarly, if we apply here at this KCL at this node B, right, then it is basically the, the process is almost the same, right? It is this V output by this R4. So that basically this okay, V output is okay. Now here the thing is that if this is V output, then due to virtual short, this will be also V output, right? So that way this is also V output. So if this is V output and the resistance we know, then we can find what is the current flowing through this 40 kilo ohm resistance, right? And this 40 kilo ohm, this current cannot be supplied from this op amp. So this current has to be come from this path only, right? So it is V output by R4. This V output by R4, that is this current, would be equal to this, V naught minus Vx, this V naught minus Vx by R5. This is equal to 0, right? Just simple KCL. So from here, we are getting? We are getting another relation between this Vx and V naught. So we have two relations and two unknowns. So from here, we can find what is the output voltage V naught. Right? Is this clear to you? Okay. So here, let us see this question number 2. Here, like you have given a bunch of 10 kilo ohm resistors and this op amp. Okay, so resistance if the values are fixed, that is 10 kilo ohm. You cannot go uh, beyond that or lower than that. Means you cannot take any arbitrary resistance value. That way resistance values are fixed. Right, design an op amp that will produce an output which is equal to this V output equal to minus 2V1 minus 4V2, right? Okay. So basically from here, what we can say it like this V output, if we take this minus as this, then it's basically 2V1 minus this or plus this 4V2, right? So obviously you can think of using some some configuration of some inverting amplifier, right? And again, further, we can also consider it like, this is like 2, then it is minus 2V1 plus this 2V2, right? So here we can also see that if we have the if we get some way this part, right, then the overall gain has to be 2, right? The loop gain has to be 2 for that inverting amplifier, right? So that is a basic guess from here. So let us see that. Okay. So to get an gain of this minus 2 for an inverting amplifier, so obviously the resistance, the feedback resistance, the what is gain feedback, it is basically minus RF by R1, right? You know that, right? This is if this is the inverting this configuration, then it is RF by R1. The gain would be minus RF by R1. So this RF has to be 2 times of that of R1. So here we are taking two 10 kilo ohm resistance. So that makes 20 in series. So 20 in series. So and here we are applying the using only this 10K and V1. Right. That way, like obviously we understand that for V1, and the gain will be means the output would be of 2V1, right? So that way this part is fixed. Okay, now we have to see the next part. Here the gain is 4 times. For V2 it is 4 times. So if we fix this 10K 10K, right, then here this resistance has to be 5K, right? But we have given only 10K, so we can add these two resistance in parallel. So that way 10K 10K becomes makes 5K, right? So it is 5K and this is 20K. So the gain is minus 4 for this V2. And you know how we have done that? We have used a superposition to get these things, right? So for V1, when you consider V1, V2 will be grounded. Find V0 or V0 1, then ground V1 and apply V2, find V0, right? And then simply add the two outputs, V0 1 and V0 2. That will give you this result, right? So it is also quite easy. So then if there is no question, then probably we can move to the next. Next problem. So here in this op-amp circuit in figure 2, we find this I naught and IS, right? We have to find this I naught, that is this current, and IS. Okay, this current, if this Vs equal to 1 volt, RL this equal to 1 kilo ohm, and plot this I naught with the value of RL, right? We have to plot this thing. Okay, so let's see then what is the total circuit here. The circuit is basically something like this, right? So here it is 0. So again the 0. So find this again the similar type of analysis every time we do. Or here you can directly see that this is an inverting amplifier, so you can find what is the output. So the output voltage is written in this way. Output voltage is equal to minus R2 by R1, right? Minus R2 by R1 of Vs. So this R2 by R1, these values are given. This Vs value is also given. Vs value is equal to 1 volt. So that way V output is 9 volt. So if this V output is 9 volt, this resistance value, this RL is given 1 kilo ohm. So if it is 9 volt, so obviously you can understand the IL. The IL direction as per this figure is this way. So which is coming out to be minus 9 milliamps. So that means actually the current is flowing from this ground towards this output, right? And that is also expected because V output is negative, so that way the current direction is expected to be opposite, right? So here this IL is minus 9 milliampere. So I think the first question was that one only, right? We no IL we don't have to find. We have to find this two, IS and I naught. So we are not yet there. Okay. So then what about this I1? Okay, because now we know now we know IL. Okay, and if we can find what is I1, then I1 plus IL would be, means from the here if we apply then KCL, right? Then we can find what is the value of I naught, right? So here what will be the value of this I1, right? That is the current which is flowing through the feedback path, so, right? So it is 9 volt. So it is 9, this is 0. So it is minus 9 volt minus 0 volt by R2. So that will give you this current, right? So you know this current, you know this current. So you can find from KCL what is this current. So which is comes out to be like this, right? So you now we know what is this current. So this is done, but we do not know still what is this IS. So that IS we have to find. So here this IS is again that no current can flow inside of them. So the IS is the same, the same current is flowing through this R1 and R2. So that means IS would be equal to this I1. So IS would be equal to I1. So that way you can find what is the value of this IS, right? Okay. Now, what is this? I think, yeah, I think that's all right for this question, for this to find it out, right? Now there was a another question, which is where we have asked to plot the I naught versus RL, right? This one, right? So to do that, now here we cannot assume what is the value of RL, right? We have to take RL as a variable, right? So take RL as a variable. So from here, what we can see from here, see this I1 value is minus 9 volt by 27K. So basically it is minus 9 by RL. This is the value of I1, right? And this, the value of this IL depends on this value of RL, right? Okay, and let's see what about the other case, that is the I1. See this I1 value depends on this. Okay, what about the other case, that is this I1, yeah, this IS, right? IS means this basically minus this I1. So this value is fixed, right? Minus 90 minus 0.33 milliamps, right? So this value is independent of RL. uh, Guys, are you with me? Hello.
Yes, sir.
Yes, sir.
Okay, so have you noticed one thing here, that while talking, means while telling this, I wanted to mean something, but what I showed here, that was a bit different. I thought like one of you will point it out, but unfortunately none of you have pointed out. So here this I1 is independent of this RL, right? But while saying that that RL value depends, RL value will be influencing this I1, I said like RL will influence the value of I1, which is not correct, right? See this, right? Are you with me in this? See this V output will determine what is the value of this RL, right? And V output is, for a particular range of this RL is determined by this resistance and this source voltage, not by this resistance, right? So that way I1 is independent of RL, right? But IL is dependent on RL, right? So how it is dependent? It is basically the dependence is like this, right? It is 9 by RL. This is the current which is flowing through this resistance RL, right? And this I naught is basically this plus this. So it is this plus this, right? Now we have to plot this I naught versus this RL. And so we know the relation, right? When you have to plot this relation over here. So from this you can easily expect, right, that the curve nature would be something like this because it is something some constant by RL, right? So it is expected to be like this. So put like RL value close to equal to very low, right? When it is very low, then what is the value of current that you are expecting? What will be the value of current when this is very low? Okay, or maybe I will ask you like this. Okay, so could you please check that what is the value? Okay, from see how to check this. One thing is that when this RL value is given as 1 kilo ohm, right? We have already found what is the value of this I naught, right? So this value of I naught is equal to minus 9.33, right? When the resistance value is 1 kilo ohm. So when this value is 1 kilo ohm, the current is this much, right? Okay, now if you add here this 10 kilo ohm resistance, right? So 10 kilo ohm resistance, so put 10. So this whole current becomes 0.33 minus 0.9, right? So that will make 1.23 milliamps. So you can see from this 9.33 milliamps, this current has significantly reduced to 1.23 milliamps. That is the current supplied by this op amp has significantly reduced when you have increased this output resistance, right? If you increase it further, then you are expecting that this value will reduce further, right? But if you decrease it, this current will increase significantly, right? Okay, here then question number 4. This figure shows an low pass filter. Estimate the value of this feedback resistor R2 such that the passband gain, okay, the passband gain of the total circuit is 100. Given that this C is equal to zero point 0.2 microfarad, R1 1 kilo ohm, calculate the value of resistor R for realizing a cutoff frequency of 2 kilo ohm, right? So here you can see here this is the signal, signal source, this V1, and it has been applied to an RC circuit here, and this RC circuit is been fed to this op amp. So basically you can consider it is this part, the remaining part, to be an amplifier, right? So signal has been fed to an RC amplifier, right? This is R, this is C, right? This is R, this is C, and you know this configuration is nothing but an low pass filter configuration, right? And what is the output here? That has been again fed to an amplifier, right? This is a non-inverting amplifier, right? Non-inverting amplifier. So whatever is coming here is expected to get an gain, and that gain will be dependent on this value resistance values, which is 1 plus RF by R1, right? Gain of this non-inverting amplifier, right? So from here, this output. So if we say like here, this output is here, this input is say Vs dash, then it will become Vs dash into 1 plus RF by R1, right? So that way we'll have an sinusoidal. Suppose it is a sinusoidal signal, or it is an source. Here we are expecting to get an and a bit higher magnitude, right? compared to this, we are expected to get in higher magnitude here. Yes, please.
Sir, the signal is AC, so
Uh,
VS dash would be zero, sir.
will
Zero.
what is zero?
VS dash, sir.
With Vs dash would be zero. So do you think that it would be zero?
Sir, yes, because no currents would be go through this OP
Op
amplifier
amp, right,
and
right.
AC
But what
signal
about this capacitor?
Yes,
This
sir. So in
Vs
AC
dash would be the voltage drop across this capacitor, right?
sir, but we don't treat it as a means that short circuit.
We
Means
don't treat it as a short circuit, that is fine, but this capacitance, yeah, we don't treat, that's why there will be a voltage drop, right? Because we do not treat it as an
sir, but
short circuit.
why, sir? Means in AC signal we are considering no, sir.
We are considering, yes, you are right. When the signal, suppose, okay, this capacitance is C, okay, for this capacitor, right? Then what is the
Yes,
impedance offered by this capacitance? This
sir.
is
R
1 by,
plus R minus. Yes, sir. Huh.
yeah, 1 by omega C, right? Okay.
Yes.
Now the thing is that when this omega is very, very high, right? At the same time, or capacitance is also very, very high, then this impedance offered by this capacitance is almost negligible, right? At that point only you can consider it to be a short. If
So,
that
sir,
is not,
like any range for omega C, like omega or C
yeah,
means
that
when we
depends.
have to.
Yeah, that it has to be very, very low. So it is not difficult to understand. Suppose this resistance is 1 kilo ohm, and if the impedance offered by this capacitance is 1 ohm, then obviously you
Okay,
can
okay,
neglect it,
okay, sir.
right?
Yes,
So you
got
have
it.
to take this. So it also depends on this value, right? This resistance
Okay,
value. Compared to
like
this impedance has to be negligible.
okay, sir. And means we can assume that whenever the values of capacitance and frequency are given, so we don't have to assume it as a short circuit.
Yeah, yeah. And that is the basically the action of our filter. That's
Hmm.
how this filter actually works. Because you see this is R and C, right? You have a signal source. When the frequency is low, then this capacitance would offer a higher resistance compared to this, right? So then almost whatever is the voltage that will drop across this capacitor. So
Yes.
that means you are getting this output. Now as you are increasing this omega, this capacitance impedances keep on falling, right? So that way the output will keep on falling, right? And that's why you will get this type of output, means this type of shape, right? Frequency, log scale, if this is the gain, or it may be gain or it may be the output, right?
Yes.
You remember?
Yes.
Okay, but here it is not an only, this part is the passive filter, right? But after that we have added another op amp, right? And we are assuming this is an ideal op amp, so this op amp does not offering any capacitance part, right? Whatever is coming here, this op amp is simply amplifying that. Right? So here this R1 is given as this 1 kilo ohm, capacitance is given, here this gain has been also given, right? The pass band gain of the circuit is 100. So pass band gain of this 100 circuit, so this is basically the gain of the non-inverting amplifier, right? So and for this non-inverting amplifier the gain is this one, right? 1 plus R2 by R1, this is equal to 100. So that will give you, and I think R1 value is given, right? Let us see it again. Yeah, R1 value is given here. So you can see R1 value is given here. So that way you can find what is the required value of R2. So once you have the required value of R2, I think the almost all the things required for to solve this problem has been done, because R value is also given, right? So here I think this part is done. Also calculate the value of this resistor for realizing the cutoff frequency of 2 kilohertz. Now this is simply RC filter part. So here the cutoff frequency equation is 1 by 2 pi RC, right? This is only for this part, right? Right. So it is like 1 by 2 pi RC equal to this capacitance value is been given 0.2 microfarad. So here only unknown is R. We have to find the value of R. That's all, right? Okay. Then let's see this question number 5. Okay, is this question clear to all of you? Question number 4. Is it clear? Question number 4 to all of you?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So let us see this question number 5 then. For an op-amp, differential gain is 100. Huh? So differential gain is 100. And so it is, remember, it is the differential gain. Huh? So it is not the differential open loop gain. Okay, it is not AOD, right? You remember that op-amp circuit, right? This, and here is this. This is AOD, right? This is output. But here, this is the differential gain, means it is the closed loop gain. It is not the open loop gain. So the closed loop gain is 100. When 1 volt is applied, and that is common to both the inputs, the output voltage measured as 0.01 volt. Calculate the CMR. So the here one thing is clearly given, that this AD differential gain is 100. The common mode gain is not been directly given, but it has been given the common mode gain. If the input is 1 volt, the output is 0.01 volt. So the common mode gain is basically V output by V in. So these two values are also given. That way you can find what is the value of common mode gain. And you know CMRR, because this is the property of op amp, right? Any common signal given to this or if there is any common signal between these two inputs, then this op amp will try to reject that, right? That's why even here you are giving as 1 volt, the output for this you are getting only 0.01 volt, right? So it can actually reduce it by 100 times, right? So then CMRR, we also know that CMRR is basically this AD by AC, that is the differential gain by common mode gain. So better to take a mod, because you do not know whether you are using it an inverting amplifier or non-inverting amplifier. So go that way, 100 by this, so this 10 to the power 4. So CMRR, if it is represented, it has to be represented in dB, then it is like this. CMRR in dB is 20 log of mod of AD by AC. So it is basically this 80 dB. So the CMRR is 80 dB for this op-amp circuit. Right? Is this clear to you? Okay. Then let's see then question number 6. It has said that consider the circuit shown in figure 4. Now derive the expression for the output voltage V naught in terms of these two input voltages. Huh? That is, this is one input voltage, this is another input voltage, and this is the output. Right? We have to find this output. So for this circuit, derive the expression for this output voltage. So for this V output, we have to find the expression. That is number 1. And number 2 is determine this output when this V input is okay. So in the number 2, the values of this V1 and VI1 and VI2 has been defined. And for that, you have to find V output. So basically, if you know the common expression, then it should not be difficult to find the part B. Right? So let us see how to solve this. So this is again the same circuit here, right? So let us assume that this potential is Vx, this internal potential. So how can we find this Vx? So Vx, if we consider this part, the first part of this, right? This one. This is an inverting amplifier. So for this inverting amplifier, Vx is the output, right? So we know that this output would be equal to minus this 10 by 1, minus 10 by 1 into this input Vi1. So that way we can find Vx in terms of Vi1, right? Okay. Now what is this what is this? What will be this V output? Okay. To find it out, how can we do that? So again, if we look for this part, that is this one, which has been enclosed in the cyan color, right? So here you can see this is grounded, so obviously this is grounded, and here, so this is basically and also an inverting amplifier only, right? But here we have two inputs, right? Vx and Vi. So we have solved this type of problem, right, couple of times. So we know how to solve it, and we know we can directly write now what will be the output, right, in terms of these two inputs. So V output would be now equal to how much? V output would be now equal to, this is 20 by 1, right? It is minus 20 by 1 into, so both resistance are this 1 so it will be 1 into this of this Vx, oh, Vx plus Vi2, right? So this V output equal to minus 20 Vx minus 20 Vi2, right? You can see from here the same thing as been found from here, right? Okay. Now what is this Vx? This Vx we have already found it is this 10 times of Vi1. So that way it will be 20 minus 10 of Vi1 minus 20 Vi2, right? So V output equal to minus 20 minus 200 Vi1 minus 20 Vi2, right? So you can clearly see this. This is the relation between these two inputs and these outputs, right? Right. These two are the inputs, and this is the output, and this is the relation between these two. Right. It's quite simple only. Though the circuit looks a bit bigger, but the solution is pretty simple, right? Now here, for the next part, these two values are given. So just you have to simply, just put these values and do this, summation, do this addition, and then we'll get what is the output. Okay, for this particular two inputs. Okay, is this question number 6 clear to you?
Sir,
Huh.
sir, in the second part, sir, isn't it a adder?
Yeah, means you mean this part, right?
Yes, sir.
Huh. Yes, it is.
So, sir, V0 will be the resultant of this Vx and Ve2.
Yes, that's what we have done it here now.
And sir, what if the resistances in the Vx and V2 line they are different?
Yeah, then you know that answer. Then it would be like this 20 by, say, if this is R1 and if this is R2, then it will be 20 minus 20 by R1 Vx minus 20 by R2 Vi2, this one.
Okay, sir.
Okay. Okay, then can we move to question number 7? Okay, so let us see that in question number 7, it has been asked like for figure 5, which is this one. Derive the expression of I3. So we have to find this I3, right, in terms of this Vi1, okay, for this. So this is also going to be the quite easy question only. So this is the question number 7. We have to find I3 in terms of this Vi, right? Okay. So what is here this I1, right? So let us take other currents. For example, this is I1, this is I2, this is IL, right? So what is I1? This is 0, so this is 0. So I1 would be equal to Vi by R1, right? What would be I2? I2 is this current. So I2 would be 0 minus V naught by R2, right? So again, these two current has to be same. So that way we are getting this output, this voltage, right? This output voltage is basically the same as that of a normal normal inverting amplifier, right? You can see that here, right? Okay, now what is this IL? 1 minute, huh? This got restarted, so it got crashed, huh? 1 minute. Oh, now it is not okay. I think now it will come. Yeah. Oh, please check. Is it visible at your end?
Yes, sir.
Okay.
Yes, sir.
Okay, thank you. So here, so we have done up to this part. V output, we have seen this is the expression, and it is same as that of a simple inverting amplifier, right? Now here, what is this IL current? IL current would be equal to V naught by RL, right? V naught by RL, right? So there are basically three currents: this current, this current, this current. So we can put an KCL, okay, right, in this node, right? Now here we know this one, we know this one, only unknown is I3. So that way we can find I3, and that would be obviously in terms of this I1 only. So this is pretty straightforward.
Sir,
Hmm.
so would we try to minimize the current that is flowing into the op-amp?
Actually, we are not intentionally trying, but you have to remember, like, this, like for the most of the common op amp, the maximum current that it can supply is up to something like 20 milliamps, right? So we will try to restrict, like, for example, if you see the previous one, that's what I wanted to show you here, but I have not explicitly mentioned that. I thought you will understand it. Okay, see this one, right? This problem. Let me, I don't have any extra color. Okay, so here this is I naught 1 versus this RL, right? So what is I naught 1? I naught 1 is the current that has been supplied or sink by this op amp, right? See this, how I naught is dependent on RL, right? So based on this your circuit design, you can actually like also fix where the output current of this op amp would lie, right? So, and for, you have to see the which op amp you are using, right? And for that particular op amp, what is the current rating, output rating, and your design should consider that part. Means you should make this value of RL and probably the other resistances such that this current is not exceeding the rated current. Is that the
Yes,
clear?
please, sir.
Okay. So let us see this question number 8. And in question number 8, it says that consider the circuit shown in figure 6. So this is figure 6. Determine the ideal voltage gain. Okay, this is an inverting amplifier, right? Determine ideal voltage gain. Okay, find the actual gain if the open loop gain. Okay. So first case, we have to find the ideal gain. That is quite easy to find, right? Ideal gain would be minus 22 by 1. It will be minus 22. So this is basically R2 by R1. Right. Okay. But then the second case, find the gain if this AOD is like 5,000, right? But here now in this case, we have to consider that this AOD, remember that AOD into V2 minus V1, right? If this is V2 and if this is V1, right? Now this AOD is not infinite, but this AOD is simply 5,000, right? Then what you have to find what is the value of gain, right? Okay. So, we have already done this type of analysis, and the final expression that has come from this type of analysis was like this, right? That the actual gain would be equal to, for this type of amplifier, is R2 by R1, right? Basically, this is, again, we are not doing the formulation. We have done this formulation. What we have to do, instead of taking like this V1 equal to V2, what you have to do, you have to consider this AOD is AOD is finite, but you can consider this input resistances are still infinite, so there is no current, right? There is no current. So considering that, if you do the analysis and find the output voltage by input voltage, it's basically come out to be like this, right? Please check if you have forgotten that in class also we have done this, right? So here, and actually you can see here, if this AOD is become very, very large, so close to infinite, so that means this part is 0, so that will give the gain will equal to minus R2 by R1, which is actually the ideal gain, right, for this amplifier. But if this AOD is not infinite, then it would be like this, right? Then what you have to do, everything, including the value of AOD is given for this. So that way it is minus 21.9. So it is expected to be around minus 22, but now it is minus 21.9. So slightly reduced. Then here, determine the required value of AOD in order to find the actual voltage gain within 0.2% of the ideal value. That is also quite straightforward. That means the gain is within 2%, 0.2% of this ideal value. So 0.2% of this means basically this one plus minus this, right? So either this or this. So take the value, and from this expression you can find what is the value of this AOD required for that. So for that you can see this AOD required is around 11,400, right? Okay. So if this part is clear to you, then probably we can move to the question number 9. So question number 9 says that for this inverting op-amp amplifier shown in figure 7, that is this one, determine this gain, basically means output voltage by this input voltage. So remember in class what we have done, this T network, that T network was something like this, right? R1, R2, R3, right? This is right. The T network was like this, but here, like we have done up to this part, right? But now here we have one more type of extension of this resistance R, right? But the good thing is that all the resistance values are same here. Okay. So let us see that how to solve. So for this question, so again this is 0, so this is 0. So again the starting process is the same. So the current I is VI by R. So this is the current, and this current would be the same as this current, right? This is I1 because till now the same current is flowing. After that it is going to divide, right? So it is this I1. Okay. So what is this V1? This V1 would be equal to this. Okay. How will find this V1? V1 would be equal to this 0, right? 0 voltage minus the drop across this voltage. So that will give you this value of this V1, right? And that is basically equal to, so this V1 is equal to minus of VI. So V1 voltage now we know in terms of this VI, right? Okay. Now what is this I2? That is this current which is flowing through this. Now if you know this V1, you know the resistance, you can find the value of this I2 in terms of this, right? Okay. So now you know this current. Okay. Now also you know this current, right? Apply KCL at this node, right? You can find what is this current. So that way I3 is also known, right? Now you know I3, you know this potential, right? So this potential minus the drop across this, right, would give you this potential. So that way you know now this potential. So if you know this potential, you can find what is this current. You already know what is this current. So if you know these two current from KCL, you can find this current, right? So if you can find this current, then you also know this voltage. So this voltage minus the drop across this, right, would give you this, right? So that way, if you know this, like if you proceed like this, finally you will be able to find in this way what is this V output, right? And if you do that, so for this particular case, this V output comes out to be minus 8 volt. Sorry, minus 8. How can it be volt? Because it is gain. It is the ratio of two voltages, right? So it should be an unitless quantity. Is there any doubt for this question number 9? Any doubt? Okay. If there is no doubt, then good. We can proceed to the next question. Then question number 10. It says that the circuit shown in figure 8 is a first order high pass active filter. Now determine how the gain of this circuit is dependent on this frequency, that is find the voltage transfer function, right? So it is basically one RC circuit, means R and C, they are connected in series, right? And it is this feedback path. So this we have to consider the total impedance of this part, right? So what would be the total, for this non-inverting amplifier gain? The relation would be the same, right? Is V output by V input would be equal to, now the instead of resistance we will write in terms of impedance. So impedance of this path, feedback path, by the impedance of this input path. So minus Z2 by Z1. So Z2 is basically R2 and Z1 is basically this two. So it is basically this one. So this will be the gain. So this is the expression of the gain in terms of this. Right? Is this clear to you?
Sir?
Hmm.
Sir, we have to consider the real part of this, right?
Real part. Okay, you saying considering for the magnitude. Yes. Yes. Mod of gain would be this mod of this part. Yeah. Only the magnitude.
No, sir.
part.
In that case, the imaginary part will also contribute, sir.
No, imaginary part will definitely contribute. Imaginary part will definitely, affect the total impedance. Right. So if you take it like this, then here you will, along with the modulus of gain, you will also get the phasor angle if you take it from here. But if you were taking this only this mod value here, then you will only get the magnitude of the gain. Okay. You will not gain the phase value from here.
Okay, sir.
Okay, then let us see this question. Next question, question number 11. So in figure 9, that is this figure. So here, see, we have connected one um, on bipolar junction transistor, right? And see, this arrow is also given, right? Oh, what is happening? Arrow is given like this, right? So, so this is a bipolar junction transistor connected in this feedback path whose base is been grounded, right? And here you have to find so that this E naught, that means this output voltage, can be written in terms of this KT by Q, ln of I in is this current by IES. IES, here I can see IE, so this should be this IES, right? So this IES, right? Where IES is the reverse. Oh, so this, no, it is not this current. So this is IE. IES is the reverse saturation current. It has been given. So that means IE is equal to IES into exponential of that mod of V of BE by VT, right? That part. So this IES is the reverse saturation current part for this emitter current. So for that, let's see from here. Here this VEB, right? VEB is basically, this is potentially 0, this is E naught. So this difference is basically then E naught only, right? Okay. Then IE equal to IES exponential of V of BE by VT, right? And if this beta is very high, we can consider IC equal to IE. So that way this current is equal to this current, right? So if this is IC, right, then I in would be the same current, right? Because no current can flow inside. So this IC is equal to I in, right? So that way, here you can see this I in. So basically, this current would be equal to IES exponential of V of BE by VT, right? And just we are doing some manipulation, this by this exponential of this. Then we are expressing this E naught in terms of this. Just a simple manipulation, take logarithm on both sides and you will get these equations. Pretty straightforward, right? Is there any doubt for this question number 11? Okay, if no, then we can move to the next question. So here question number 12, it says that if an op-amp has a slew rate of 5 volt per microsecond, find the full power bandwidth for a peak output voltage of 5 1.5 0.2. This is quite, again, but just only write the formula, put the values, that's all. So full power bandwidth formula is this, this slew rate by 2 pi into V naught max, where SR is the slew rate and V naught max is the maximum peak amplitude. So everything is been given, just put the values and you will get the you will get the full power bandwidth, AP bandwidth, right? That's all. Just keep for different values. This one. Pretty just remember, I think no need to remember also, right? Because you know how simple was the derivation, right? Take any sinusoidal signal, take a derivative, right? And the derivative, make the derivative equal to the slew rate. That's all, right? Okay, then let us say question number 13. An amplifier system is to be designed to provide an undistorted 10-volt peak sinusoidal signal at a frequency of 12 kilohertz. Determine the minimum slew rate required for that amplifier. Again, here this full power bandwidth is given, right, at 12, this one. Peak output voltage is also given 10 volt, right? And here use this formula, again the same formula, and find the slew rate. That's all. Right? Is this clear to you? Question number 13, please check. I think it is pretty straightforward, but you also do check it once. Fine. Okay. So question number 14 is on this open audio amplifier with an open loop gain of this dominant tone frequency. So this part probably not required for because I thought initially I will be we have not discussed much on this, so we can neglect this question number 14. Okay. So I think this question number 15 is the last. So let us see then question number 15. So for figure 10, that is this figure, neatly sketch the output voltage, V output voltage when V in is a sine wave of frequency of amplitude 2 volt, that is 0 to peak. Consider the op amp ideal and 0 voltage drop across the diode in forward bias. So here the only thing is different is this, we have also one diode, right? And after that we have this V output voltage, right? So you can see this is basically the circuit, right? And here it is 1 volt, 1 volt. So when the diode is in forward bias, then no voltage drop across this diode, means you can consider this to be short, right? And when it is short, right, this, this is an what type of amplifier? This is an inverting amplifier, right? And with a gain of 1 by 1, so gain of -1, right? So this is an inverting amplifier with a gain of -1, right? So but when this V in is negative, right? Okay, so this is an inverting amplifier, right? So inverting amplifier means for the positive sinusoidal part, the output would be the output is expected to be negative, right? But during that negative part, diode will not conduct, so you will not get any output. So for the positive half, you will not get any output, right? But what about in the negative half, right? For the negative half of the input, you will get an output in the positive half, and here you can see for this positive during the positive half, this diode conducts, and our this analysis is validated, means this analysis is valid, that this is shorted, right? And this will behave as a normal non-inverting amplifier, right? So basically, you can resemble, I mean, you can obviously you have understood that this is nothing but the precision rectifier only, right? So it is that precision rectifier. So means, so that means, if this input is like this, see, if this input is like this, during the positive half, you don't get this output, right? You are expected to get no output here, right? For the negative half, you will get this output, which will be equal to 2 volt, because there is no drop across this, and the gain is also 1, right? Again, for this negative half, you will get the output here, right? So this is the way you are expected to get this output. So that means if I try to draw it like this here, right? Only for this part you will get this output. This part you will get this output. So this is basically an precision rectifier. Okay. Now I think little bit more analysis on this. So when this V in is positive, right? Then see what happens. When this V in is positive, it is quite clear. Then the diode is off, right? Okay. So the diode is off. That is fine. But here this is a V output. So if the circuit is only like this, then if you are taking the, suppose adding an multimeter, then obviously you will not get anything right from here. Or maybe the other way I can explain it in this way is like this. Okay. See, when this V in is positive, right? So when this V in is positive, then what is happening here? So when this V in is positive, so that means for this part, right? Or for example, for this part, right? So for this part, this diode is open, right? So you have given here this positive part, right? And this diode is open. So here, what will be the output if suppose this RL at this load there is nothing, right? Then whatever you will give here, right, you will get it here. Are you with me on this?
Yes, sir.
Right, because it is, see, it is the simple this resistance, right? Here is resistance, and here this part is connected with this. No current can flow inside op amp, right? So basically, like here, if you have connected, suppose in simple non-multimeter, okay, then whatever is this voltage, this will take this will measure the same voltage only, right? If it is not connected with anything, right, it's simply suppose floating, then this voltage and this voltage would be the same. Right, okay. But suppose now you have connected at this output some resistance, right? This RL value, right? Then what will be the value of this V naught? Then V naught value would be equal to, say, this is R, this is R. So V naught will be equal to RL divided by 2R plus RL, right? So now depending on the value of this RL, right, this output would vary, right? So if this, see this, if this now RL is very high, right, very high, then almost V output would be equal to V1, right? And that is also the same thing, because when you said, like, if you are connecting here one multimeter and nothing else, that means this resistance is type of infinite. So when this resistance is infinite, then V1 would be equal to V naught, right? Okay. If this RL is much lower than this R values, right, then this voltage drop V output here would be almost negligible, right? So that way, in this output side, so what we have said, like, it is, you are getting an output for this and you are not getting output for this. But if you think it bit carefully, then you will also see that the output, if you are taking it across, means from here, taking the output from here, right? Not like our previous case. Okay, our previous case means for the precision amplifier. Okay, okay, can you please tell me, for the precision amplifier, from where we have taken this output?
Sir, from the terminal which is directly connected to op-amp.
From the terminal which is directly connected with the op-amp, are you sure? Are you sure? You forgot. See, for precision amplifier that we have studied in the class is something like this, right? It was something like this. It is actually an buffer, right? For for buffer, in between we have placed one and diode, right? So that way it is not this configuration. So this situation will not arise, like whatever situation is arising here, because now it has been connected with the inverting terminal and you have a feedback path between this input and this output, right? And if you are taking the output from here, right, then this particular issue will come, right? So you have to be careful here in choosing this RL for this particular circuit, right? So you can see from here. So if this RL is very high, then you are going to get, for positive half, you are going to get an output which is like this, right? If this RL is very low, then you are going to get an output probably like this, right? So depending on the values of this R, you can get these different shapes for this positive half, but not for this one. So that way, saying it to be really as an like precision amplifier, I don't think that is a pretty statement, pretty good to say it like that, because even though we have mentioned it's a type of inverting precision amplifier, it's not actually that way correct, right? Because even for the positive half, you are getting some output, so it is not able to clip the other half of the sinusoidal signal. So that way it is not actually a good rectifier. Yeah, but it shows some property similar to that rectifier if this RL is pretty low, right? Then probably you will get an output something like this. Right?
Sir,
Huh.
sir, if
Yes.
RL is infinite,
Hmm.
sir, then we can treat it as an open circuit, right?
Right.
Sir, in that case, sir, how you can say that V naught is equal to V1? Shouldn't there be any drop across these two resistors?
Yeah, if there is any current, there will be drop.
So if we apply the virtual short concept, then there will be current.
Okay, so suppose if I want to measure the voltage here, right? So which thing Means what we should connect here?
Sir, nothing. We assume RL is infinite.
We assume RL is, yes. Oh, so suppose RL is infinite, right? Then if you just simply suppose, if you want to have some, suppose some mechanism to probe this voltage, okay, and for which there will be no flow of current, okay, through this, then this V1 would be equal to like this voltage, and this voltage will be same, right?
Yes, sir, but in special case, na.
Sir, there would be no current in the circuit, sir.
There will be no current. So if there is no current, right, then the potential will be the same, right?
Yes, sir.
So the potential at the midpoint will be 0 due to virtual short. So there should be current.
No, at that time feedback path is not complete, right? You see, when this
Okay,
situation
okay.
arises, right, this feedback path is not complete, na?
Okay.
Okay, so can we take then here 2 minutes break and come and start, I think, with this 15 number question. We have finished almost all the questions for practice paper or practice paper 6. Right, so we can start the digital part, but maybe before that 2 minutes break. Okay, so please join in 2 minutes. I will take some water and come back. So, and also I will end this recording here, okay? And I will start recording from that, from for the digital part separately.